There's nothing more important on this planet than water. It's the lifeblood of everything from ecosystems to plants and animals, agriculture, manufacturing, and human development. Water is perceived to be the limiting factor in human development around the globe. And in the western United States, we've been experiencing extremely rapid population growth and agricultural development at the same time when we've seen diminishing water supplies in our rivers. And this confluence of factors where you have increasing growth, a desire for people to live in beautiful places throughout the West, and declining water supplies puts a tremendous pressure on our river systems, both in terms of how they deliver out of the mountains and how we then transform it and put it into pipes and agricultural production. So when you look at a stream like we're standing in here, you have to think about the waters providing ecological services to aquatic life, riparian vegetation, and riparian health. And then it's being delivered downstream for domestic water use, municipal water use, people, plants, animals, agriculture, and eventually large cities. Everything is inextricably linked. Today we're out doing some observational hydrology. We're going to measure velocity and water quality, 0.26 meters per second. We're building hydrologic models that appropriately distribute water into surface, ground, and subsurface water. Our models represent the topography, the soils, the vegetation that's on top, and it takes climate, rain, snow, and then it predicts how that rain and snow is going to move into the surface water in our streams, go into the soils, and ultimately end up in the groundwater. We take computational models that are very useful at larger scales to understand how changes in land management, changes in population, and changes in climate will affect water deliveries.
Most of the rivers in the western United States are over-allocated, and what that means is more water rights have been granted than there is water to meet the demand in most years. The equitable management of that water requires accurate flow measurements and model predictions. One of the main problems with flow measurements in rivers is the sediment they carry tends to accumulate behind structures such as weirs that we use to measure flow. We're doing a study in the laboratory to see what the effect of that sediment is on weirs and to better understand how we can make more accurate flow measurements by understanding that effect. We have a system of pumps that recirculate water over the structure, and we can very accurately, using some large weigh tanks, measure the exact flow rate that's going over the weir. And then we have ultrasonic water level sensors, which are essentially electronic tape measures, to measure the water surface profile. We do these tests with and without sediment to see what the effect of the sediment is and to determine how we can correct for the effect of sediment. Niels Bohr, the famous Danish physicist, said predictions are difficult, particularly when about the future. And making predictions about the futures of water resources in the West is very, very fraught with a lot of challenges. Climate, land use, and population change all exert pressure on water resources. What we have to do is simulate a large number of possible scenarios to see what the outcome might be. We are attacking the problem on three fronts, with field research, lab studies, and computer model development, all of which help each other.